We now have most of the basic definitions of interest rates under our belt, but there are some additional things we need to discuss before we can get into the economics of credit markets. While the interest rate indicates the cost of borrowing to the borrower, what a lender makes on an asset can be a different story. This is what we refer to as the discussion of rates of returns versus interest rates. The reason why there can be a difference between the two is that while a lender is entitled to fixed interest payments contractually determined by the price they originally paid for the contract, the circumstance that assets can be sold in secondary markets means that price changes for an asset over time also can affect how much a lender makes overall. How much a lender makes in total for each $1 invested in a credit instrument is then given by its total rate of return instead. Now we'll illustrate this in some more detail in one of the practice problems. For now, we'll only walk you through the general logic. Say a lender buys a coupon bond in period T, holds it for one period until T plus 1, and then resells it at the prevailing price at that point in time. In this case, the dollar amount the lender receives is equal to the coupon payment, C, plus the resale price of the bond, PT plus 1, B, and from that we subtract the original price they paid. That's their dollar return. The rate of return in analogy to interest rates is then found by dividing by the initial price, and it indicates how much did I make for each dollar I originally paid for the bond in this case. We can decompose this equation in two parts since they share a common denominator. The first expression here is the coupon payment divided by the bond price. Now this is a proxy of the interest rate on a coupon bond known as the so-called current yield IC. It's not exactly equal to the yield to maturity and can be different close to maturity because it ignores the face value payment. But as long as a coupon bond has a significant amount of outstanding maturity, it is a relatively accurate proxy. The second component over here is a structure you should have seen before. It is the price in T plus 1 minus the price in T as a fraction of the price in T. And this is simply the percentage change in the price from T to T plus 1. Now, this can be positive or negative depending on how prices develop, and it's usually abbreviated using a lowercase letter g. If it's positive, it's referred to as capital gains. If it's negative, it's referred to as capital losses. The rate of return is thus a function of two things. It's the interest you earn plus or minus changes in the bond price if you are to resell this bond over time. Let me give you a simple, rather exaggerated example. Say you buy a bond with a coupon payment of $200, which would be tremendous, usually it's much lower than that sells at a price of $1,000 today, and then you resell it at a price of $1,200 tomorrow in T plus 1. That too would be a tremendous increase in prices. In this case, the coupon payment and resale price exceed the initial price by $400, which is a 40% fraction of the original bond price. So your rate of return in this case would be equal to 40%, needless to say much higher than the initial interest payment on the bond. Now, capital markets in practice are not typically this generous unless you take on high risks, as we will see in the coming weeks. However, capital gains or losses in bond markets are common. In this context, keep in mind again that the price of a bond and interest rates are inversely related. When the yield on a bond increases after you buy it, it's equivalent to saying that its price has fallen. And if the yield on a bond decreases after you buy it, it's equivalent to saying that its price has risen. Now, what's the implication of this logic for the rate of return? Now, whenever interest rates are increasing after you purchase a bond, you as the bondholder incur capital losses if you're trying to sell the bond. Even if you don't sell it, you still make a calculatory loss because you're locked in this lending contract that now pays a lower interest rate than what you could make elsewhere in the market. If you had the money available instead of holding it in investment, you could reinvest it at a higher interest rate and make a larger profit. So irrespectively of whether you sell a bond or not, you will still make an economic loss. Due to financial math, details which I will not discuss here, the further away from maturity and interest rate change occurs, the larger will it weigh on capital losses or capital gains. And as a consequence of that, it is entirely possible that a bond yields negative returns for this reason, even though it pays a fixed positive interest rate. Now, this type of risk is known as interest rate risk, and it is an important component of bank risk management. It's one of the reasons why many interest rate derivatives exist, like interest rate futures, interest rate forwards, or interest rate swaps. We will return to the notion of interest rate risk a little bit more at a future point. Just be aware that bonds are worse investments whenever interest rates are expected to increase in the future, and they're better investments whenever interest rates are expected to fall in the future. Switching gears to our final subject for the week, be aware that interest rates, as we have defined them, are typically nominal. That means they're written in dollar amounts. A standalone bond contract is written in nominal terms. It does not adjust for inflation. As is the general convention in economics, nominal interest rates or rate of returns do not control for inflation, while real interest rates and rates of returns do, and we believe, generally, that economic agents act more based on what they think real variables are than what the dollar amounts are. Now, in practice, how are the two related? A fundamental relationship in finance is the so-called Fisher equation, named after Irving Fisher, which simply states that the nominal interest rate I is equal to the real interest rate IR, also sometimes just R, plus expected inflation pi E. For instance, if you pay 5% nominally on a loan over a year, but the expected inflation rate is 2%, you effectively only have to pay 3% adjusted for purchasing power. The same logic carries over to rates of return. Now, in theory, there's a little bit of a cross term here, but it is so small that we typically ignore it. It's basically zero. Oops, sorry about that. This keeps happening. I want to show you this final graph. Sorry about the technical difficulties today. So final sort of follow-up on this idea of nominal and expected inflation rates. When contracts are written, parties do not know what the actual future inflation rate is going to be. Instead, they have to form an ex ante, that is, before the fact expectation. The nominal interest rate is a function of this expectation. Again, nobody knows what actual inflation rates are going to be. As a result, we really don't exactly know what ex ante real interest rates are. We can take nominal interest rates, like in the case of Canada here, and then we can subtract actual inflation. But the problem with actual inflation is it's an ex post variable. It can be different from what agents believe was actually going to be the case. So it is quite possible that if inflation is different enough, you get negative real interest rates, which means someone is paying a lender to lend to them. Someone is paying a borrower to borrow from them. There are some instruments like the aforementioned TIPS inflation protection treasury bonds that have yields which adjust to inflation in a Fisher type sort of logic. And one can in principle estimate expected inflation from the difference in adjusted treasury yields and non-adjusted treasury yields. In practice, however, the implied inflation rates tend to actually be rather bad estimators of actual inflation in practice. And this suggests that there's something going on in the market that doesn't quite capture inflation expectations accurately. The other option we have are survey-based measures, such as that of the University of Minnesota and Michigan. Although these two are bad predictors of inflation rates in practice. All right. I realized there were a few technical difficulties this time. I apologize for that. I had to do this in the middle of the night. I appreciate the patience. In the meantime, this is one of the more technical aspects of what we covered and will cover throughout the semester. Next time, we will go more into the question of what the determinants of interest rates are. Thank you for your time and patience. I will talk to you soon.